Well, good evening everyone. I hope my microphone sounds alright. So today I'm pretty much gonna show a bit of how I do and what I use when I take images of integrated circuits. So this is just the way I do it. It might not necessarily be the best way or even a good way. Most of this is self-taught and discovered from YouTube channels, Robert Baruch, John McMasters, etc. There's quite a few really good people doing this on YouTube and on the internet in general. John McMasters' wiki page at Silicon Zoo, for example, is a fantastic resource. So, to show some of the tools, let's see, change the view. So there's my microscope. It's a normal AMScope. It is a metallurgical microscope, meaning it doesn't have a light shining through what you're trying to image. It actually shines light through the objective. So the big black box on the back side of the microscope is actually a light source. It shoots into a prism that then gets redirected into the objective. So you're actually shining through the objective that you're using to image things. Obviously, since metal can't be shown through in most normal circumstances. I have modified this microscope quite a bit, actually. So the X and Y axis, so the actual table, has been modified to have motor control. Let's see if I can move the camera down a bit. There we go. So it's motorized using two stepper motors and belts going to the OEM table. What do you call it? Manipulators. And also on top of the actual table, I have mounted a tip tilt table to allow it to tip and tilt. So that's basically set up so I can arrange for the silicon dice to be planar with the objective. As I move the table, I don't want the focus to change. And that basically allows me to do so. I still have a few issues, teething issues, etc. It is what it is. Camera-wise, if we're moving up top, it's a trinocular head. So I can use these binoculars when I'm working on my own. And then I have a camera mounted really up top here. That's an AMScope 10 megapixel camera that I'm using right now. I also have, let's see if I can dig it out, which is my usual way of doing this. Oh, it's gone missing. Oh, isn't that typical? Yeah, I thought I prepared. Oh, there it is. So another handy trick which I discovered is this is a Raspberry Pi high quality camera. Come on, focus. There we go. So this is a Raspberry Pi high quality camera, the one they released, I think it was early last year. It has really good resolution. It's a Sony CCD sensor inside. And best of all, it comes with a normal C mount, which is what most microscopes actually use. So this one allows me to just mount straight onto the microscope itself using the adapter I got from AMScope. I should probably use manual focus for this. Oh well, we'll live and learn. The other thing that I have done, as you can see up here, is I have a Raspberry Pi 4 mounted on the microscope together with a 7-inch touch display, and that's one of what I usually use to do the imaging, etc. Right now I'm using the AmScope camera to allow the streaming to work better. Additionally, let's see if I can show this one. I have made my own control board to run the microscope. It's very rudimentary, it's just a prototype, so it has an ESP32 microcontroller, a voltage regulator, and 4 TMC2208 stepper motor controllers. They're connected as a 4-axis controller, so you have X and Y axis and then A and B. A and B is the tip and tilt, and X and Y is for the table to move. So I'm just gonna power that one up while I'm here. There we go. It's pretty quick to start. The way I usually run this, if I'm exploring manually, I will use the web interface of the firmware of that ESP32. I'm running a port of GRBL, the CNC controller software, to the ESP32 on it. So it has a nice web interface, and I just connect to it over Wi-Fi and use the jog control that's built in. It works pretty nice. I can also telnet straight to this ESP to run G-code, and most of the software to do this runs on the Raspberry Pi itself. This is very convenient because when I'm using the Raspberry Pi camera, I can send the G-code to do a move, take a picture, then send another G-code to move again, take a picture, etc. And the other nice thing with the Raspberry Pi is there's pretty nice ports of OpenCV to it, so I can do a lot of more intelligent things, shall we say, with the images. I can do edge detections. I'm currently working on using autofocus to automatically set the tip and tilt correctly when I add dice to it. I'm also planning on, at some point, motorizing the Z axis of the microscope by basically mounting a stepper on the fine adjustment control of the microscope. So that's pretty much as far as the imaging equipment goes. Let's see. There we go. Just have a look. There we go. So when you have it all, I have it all connected up to stream right now. So what I will normally do is use a screen similar to this. So I have the AmScope application. Since I'm using the AmScope camera, I'm using the AmScope application. It's live streaming the video from the microscope using a USB-free connection. And here I have basically a jog pendant, the control for the ESP32 stepper control. So with this one, I forgot that I didn't have it powered on when I'm connected. With this one, I should be able to move things around, and this does not work right now for reasons. What's going on? Is the microscope camera actually? Yep, the microscope camera is fine. So why is the steppers not doing a typical demo effect? There we go. Now it actually managed to get going. So this is all to basically just show on the stream. Normally I don't use auto exposure. Same with the white balance. I basically try to configure everything to be manually set to get even consistent color levels on the captured images. The primary reason behind that is simply because when you later try to stitch the images together, if you have it all set to manually, you get a nice even color across all of the pictures that you take, so you can stitch them together. I am very bad at the stitching process. I've been slowly trying to learn how to use Hugin to do this, which is a very nice piece of software. It's not the easiest to use though, so most often I end up using the Microsoft image ICE. I can't remember. Image Composite Editor, yes. It's more of a throw it in. If it likes the pictures that you throw at it, it will generate pretty good results. Issues with the current setup, I would say, is I have pretty severe vignetting at times. So if you look at the image currently from the microscope, it's sharp in the center, and as you go out to the edges you see it getting more blurry. As far as I understood this is almost inevitable because the light at the edges has to travel further inside the microscope compared to the light in the center of the image. So you kind of get that bit of a blurriness as you go. The way I work around this is basically I take a picture and I cut out the center part of it, and then I just make automated moves to match those. I try to get 50% overlap or so between those pictures as I capture them. So that's about it for the image capture and the way I work with the microscope. I have 4 levels of magnification. This is the lowest. Hang on. Which is a 50 time magnification. I have 100 times magnification. I need to check why it's changing the focus all that much. It shouldn't normally. And a 500 times magnification. These are all straight from these magnifications. These objectives are all straight from Amscope, the same manufacturer. And I also bought a 200 times objective, which is from Olympus. That's probably the main daily driver. Mind you, the images that you see on the screen is scaled down low resolution live imagery. If I take a snapshot, the resolution is going to be a lot higher. So if I just take a snapshot, you can see that I can zoom in quite significantly before you start getting actual resolution artifacts. I wonder, do I have? Yeah, there we go. So this is the actual image size captured. So it's quite significant. The magnification that you get. The 200 times is for many things overkill, but when I have it, when it's set up correctly, it generates really nice images that you can use to reverse engineer pretty well. And I noticed another issue, and you can see it here. It's very sharp on this side of the image, whereas if I start going over to the right, it gets blurry, and it's the same. Top is sharp, bottom is blurry. This is due to the tip and tilt not being correct. the distance and the focus depth of the microscope is so short, and the thickness of the die and the layers of the die is so thin that if you don't have it absolutely level, you get these issues. And much of my setup time is actually spent on making sure that I get this leveled correctly. So I think that's pretty much it as far as image capture goes. When it comes to decapping ships, there are many methods of doing this. The most commonly used, I would say, among professionals is using acids to etch away the epoxy, because the ship encapsulation is made out of this really hard epoxy. And ultimately, the IC inside is just a small bit of glass. That's ultimately what it is. It's fairly fragile. It's not horribly fragile, but you can't just crack the chip open as is, because you will also crack the die. So most people use acid to get rid of the epoxy, and remember, this epoxy is actually designed to withstand all sorts of environmental horrors. Oxygen is a horrible chemical in actual reality. Is highly corrosive. So the epoxy packaging is made to withstand a lot. So accordingly, the acids you end up having to use are not the nice and friendly kind of acids, as acids go. The most common used, to my knowledge, to open up these dyes is red fuming nitric acid, which is horrible stuff. I mean, it's truly a horrendous acid. On top of that, for it to be really effective, it has to be at least 60 degrees centigrade. So now you're dealing with hot fuming red nitric acid, which is just no fun. No fun at all. So I'm actually using a slightly different method. I will show it live, which I found on YouTube. I will add a link to the comments later. Where they basically use hot air to heat up the epoxy resin. If you heat up the epoxy resin enough, it becomes embrittled, and you can break it off usually without affecting the die. It doesn't always succeed, and the other difference is, using the acid method, you can actually get to the position where you have a working ship still in the packaging, but with the die exposed. You will never do that with the method that I have, that I'm using. The advantage of the method I'm using is I don't need anything except a pair of pliers and a hot air reflow station. No acids involved, which is nice, because acids are... If I could afford a fume hood and had room for a fume hood, absolutely I would work with that instead. You just have to make sure you take the correct security precautions, etc. So, just to show some of the other tools. No, let's do that later. Hope I'm still audible. Yep, there we go. So, what I do, let's change to the camera again. I'm just gonna flip it around. What I usually do is I use my hot air rework station. This is just a standard issue El Cheapo Chinese model. I think most of us will have one or two of these floating around somewhere. I use a couple of pliers. So most often I use these. One which is just a normal pair of serrated pliers, which I use to, oh come on, focus, there we go. A pair of normal serrated pliers which I use to hold the ship package in place. And I have a pair of flat nose unserrated, so they're just completely flat. This is what the tools I normally use. So let's see. I do not have any Apple ships at this point. I'm still waiting for some deliveries on that. So what I will do instead is use something I'm fairly familiar with. I got a nice package of dead Commodore chips from Rob. So let's see what goodies we have in here. And we will crack one of these open and have a look at it. So there's that CIA. Oh yeah, these are always nice if you can get a hand of them. This is a ceramic package. And what you can do with these is if you put a chisel right at the edge of this lid, you can chisel the actual small metal lid here off, and that will give you the die fully exposed. That's the cheap and easy option of doing it. But a lot of ships are not available in this type of packaging, so we have 6569, so a VIC 2. 8501, so that's a plus 116 series CPU. We have a bad PLA, a SID chip, surprise, another CIA, SID, PLA, SID, SID. Yeah, the SIDs tend to go pretty quickly, and a bunch of logic and memory chips. So, you know what? What we will do this time is we will grab the 8501. I'll put these back in here. And most often, as long as the ship has not had a catastrophic failure and cracked the packaging, they're usually gonna be good for this type of destructive reverse engineering. That's not gonna be a problem. So let's see, what I will do is I will turn on the hot air station. I'm just gonna put it, I usually just put it lying down like this. I have it set to 500 degrees. About the microscope out of the airflow a bit. I'll bend the legs up straight. It makes it easier to handle the ships. It's not hugely important. It's just for convenience. And yes, it feels horribly wrong the first couple of times you do this. You're not used to just willfully destroying ships like this. So, I will hold on to the ship. So the other thing, and this comes with a bit of experience, you want to try and know about where the die is. Yeah, sorry about that. I'm still learning this whole streaming malarkey. I'm using a wireless headset so I can work, and it keeps just turning itself off. So, anyways, what I will do is I will just hold it in the stream. I have it set to 500 degrees and full blast. So if I were to try and crack this right now, using just the pliers like this. I can't do it, it's just too hard. So, if I keep blasting it with hot air, I usually just flip it around a bit to get a nice even temperature going. Once you get to a specific temperature, you will start hearing little crackling, popping noises coming from the packaging. That's, as far as I can understand it, it's basically small water intrusions. There we go. Now it's crackling a bit. You don't want to overheat it. So I usually just, once I get to the crackling point, I can now grab this and just gently bend it. And you can see how it just cracks away. It gets a bit stuck because of the ship lead carrier inside. So that's fine. I will just keep on working. See if I can get a better camera angle at this. Try and not boil the camera, of course. There we go, that's better. So you can see the ship leads inside. So these are basically the connections coming from the legs going to the die inside. Once you get closer to the die, they're connected to the actual ship itself using bond wires, which are really, really thin wires of gold. It's a really interesting piece of machinery to look up. Bond wire machine. You can look it up on YouTube. These machines are impressive. So I had a bit of a crackling there. Flip it over. And some more cracking, so I will just bend it. And it becomes really soft actually once you do this with the heat. And now you can actually start seeing, let's see, come on, focus, damn it. Now you can see how they actually start converging right here. The die is gonna be right in this area here. It's a bit hard to see on camera, but I can actually see the die starting to slowly peek out. It's mounted on a small metal plate, which is then put inside of the packaging itself. And this is the part where you really don't want to overheat too much, because you can actually damage the die with too much heat. Yes, this method is pretty brutal. But with a bit of practice it actually gets pretty good results. So now I will slowly start cracking just on the outside. And here you go. You can start seeing the little metal plate I was talking about, which is right here. Oh, come on, focus. There we go. So this metal plate here will have the ship on the other side. So the ship is actually on this side. So what I'm going to try and do is we will crack a bit more around here. Wouldn't surprise me if I ruined this one just because I'm streaming it. starting to peek out a bit. You also want to be careful. You don't want to bend and crack it when you don't have heat on. The die tends to get stuck on the epoxy itself. And now you can really start seeing the carrier in there. The die is going to be right on the other side of that. So let's see if I can crank it just a little bit more. And there we go. Now it's actually going places. Come on. Come off it. This is usually the part where I tend to bungle it up. It can be tricky to get the die to let go of the epoxy resin itself. This one, sometimes it just pops straight out, pretty as a bird. Other times, like this one, it can be incredibly stubborn. And there we go. See how you look. So, poop. Now it's actually come off, so you have the die sitting right here, still in the epoxy resin. Come on, focus. There you go. It's still sitting there, and this is pretty dangerous, this part. It didn't come off as nice as I wanted it to do. So, let's see. I'm gonna go get a... They're over here. Can never have too many pincers. So I'm gonna grab this one. Try and not overheat things. And see if I can't just gently nudge the die off here. And there we go. It's come off. There we go. Let's let the hot air station cool down a bit before I turn it off. Let's see. I will just use a microscope slide and a pair of needle nose pincers. And here we go. It might be a bit hard to see, but there's the die. So I can turn the noise machine off. There we go. Get rid of some of this craft. What I usually do, I try to actually do multiple chips when I work on it like this, because you make a mess and it's nicer if you can just clean it up once as you go. So What I usually do to store them in the interim is I have these little test tubes like this, which I then basically just put the die in and put a label on it to state what it is inside. So, but we have this one here. I'm just gonna bring Mr. Microscope back in. We'll put it in at come on, move into place, will you? There we go. I will put that into the microscope. We can change it back. And there we go, our first view of an 8501 CPU. I tend to normally just use the binoculars to focus in. And there we go. That should be a bit more focused, I hope. And yeah, the rotation is another one of those things. There we go. And now I can start moving around on it. It will lose focus as I move. That's pretty normal because I haven't leveled anything. And what I usually try to look for first whenever I do this, you want to find any form of identifiers. And there we go. 8501R1. So let's increase the magnification a bit. I'm just gonna pop over and do this on through the binocular. There we go. Grab this. Oops, that was too large of a move. And usually around this one, the ship marking itself, what you can usually find around ships in general is, I don't usually see them here, but that looks to be one. So this thing here is a test transistor, I think. Let's see if we have anything else on the die. That looks interesting. So just to go over, yeah, up here we go. There are a few things that you want to look for. Up here, for example, we have these numbers here. I'll zoom in a bit. So these numbers here, you can see a 0. There is a 1 and 2. 4, 5, 6, 7. These are the layers, or rather the masks, that are used to manufacture them. So you have the base silicon ingot that everything is placed on, that comes from the wafer, is called the substrate. You have doped parts of the substrate, that's mask 0. The other ones here are going to be glass, they're harder to see. You will have a polysilicon layer, I think that's 4 here. You will have a metal layer, 6. The metal layer, this is an NMOS process from Commodore, so I'm fairly familiar with the layers. It's really old technology, this is late 70s type chip technology. So this bright white color here is basically the metal that's used. Yeah, green is going to be the polysilicon in this case. The various components of this is of course used to actually make transistors. And the structure that you see here are also something typical that you will find. That's a test transistor. Let's see if we can go in a bit more and have a look at that one. I just wish I could show the clarity I get in my binocular side. So this is basically a huge transistor that they have made to test that the layers are aligned correctly when they make the chip itself. So after they manufacture, they can have a look at the numbers to see that they're all neatly aligned, etc. And they can use probes on these pads that you see here, these 8 pads here, to verify that this transistor they built here actually works. So it's a quick and easy way for them to do functional testing at the most basic level. I'm sure they do a lot more testing. This one is primarily just to validate the process and the layer alignments. Going back out again, is there anything else that we can see? Yes, we can talk about that as well. So these squares you see here with round things on them, those are bonding pads. So that's where the little gold wires come and connect. So these are basically one-to-one pins on the outside of the ship. They're not always connected, but when you do a decap like this, you can actually see if there's been anything bonded on the pad. The black hole here is where the bonding wire was ripped off when I did my brutal decapsulation. Yeah, there's one. You can see this pad here. Let me just focus a bit. The reason it loses focus is because I haven't leveled the chip. This pad here has never had a wire bonded to it. So that was never connected to any pins. And here's another one. There are a few other things I can actually tell from this because I'm used to the Commodore processes. These pins here are outputs. These pins here are inputs. I will explain that a bit later. Here are more outputs as well. The other thing I'm looking for now is the power inputs. So here's one, for example. You can see a connection and it goes straight into a really large metal field like this. So this is either ground or power. There will be 2 of them. Somewhere. I think that's the other one. But that might just be an output pin as well. It can be a... no, there it is. There's the other one. So finding those 2 can be really useful in identifying where the pins are connected on the die compared to the outside of the chip. They're usually in numeric order going around because you don't want to cross the bonding wires. Not much, at least. And finding where the ground and VCC pins are will usually help you orient which pin is where on these dies. There are a few other things that you can actually see if you look at the overarching structure of the chip. Usually a good idea is to look for the generic areas of things. So if I look around here, you can see this structure down here. That is a very regular type structure. So let's zoom in on one of those and have a closer look. I have a hunch I know what it is. But I might also be wrong. I'm not a professional at this. It's a bit large. I thought it was the mask ROM holding the instruction to code. But it's a bit too large for this, and I can't really see any obvious structure that sticks out to me straight away. But it might just be, actually. Yeah, it probably is. So what I can see, and you probably can't see all that great, let's go in even higher. See if I can't show off some of it. Yeah, there you go. That's a bit better. So I can start showing a few things on here to start help decoding some of what you're seeing here. So the white stuff here is metal, as we discussed earlier. In the Commodore ships, it's usually, I think it's aluminium, which has been sputtered on there, so it's basically been vaporized and allowed to settle on the die. You have the green stuff that you can see here. That's the polysilicon layer. So that's basically a sputtered silicon as well. It's a pretty poor conductor, but it is a conductor. And if you look really closely on this one here, you can see that there's a little circle on it. So what you're not seeing on this picture is glass. There's multiple layers of glass sitting on this. And the little circle that you see here is basically the equivalent of a via on a PCB. It's a hole in that glass to allow the polysilicon to connect with whatever is the other part. So the background is all gray, but there are two different kinds of gray separated by these black lines, as you can see. And what that is basically the substrate and doped substrate. Which is used, I'm gonna see if I can find a bit of a hard chip to actually see anything on. Might be better if I pop in a different one. This one has also not been cleaned. I tend to clean things in my ultrasonic. There's a lot of little speckles and dots on it, like these, which is basically debris from my process. The little dots here are more vias connecting the metal layer to the layers beneath. Nothing more fancy than that. So, yeah, let's do that. I'm gonna put this chip aside for now. I will grab. Let's see what we can have a look at. I have some I've done earlier, but I don't know which state they're in. This is probably a Commodore 128 PLA. Let's have a look. Nope, this is a C64 Super PLA. But here you can actually see, I just want to show this. This is a remnant of a bonding wire. So this is a piece of gold wire that's stuck on the pad, and this was connected to the lead frame carrier. I haven't put this in the ultrasonic cleaner, obviously, because that tends to rip these things off straight away. But it's pretty cool to see. You can really see the gold if I start focusing on it. You can also see the rest of them are really still connected on the pads. So this one has not been cleaned at all. So that's a C64C PLA. the Super PLA. What else do I have? This should be a 128 PLA. Nope, this is a 128 MMU. That's fine with me. Let's see so I can get it level. There we go. So I will use this one to start showing some of the structures. This is Commodore's NMOS process. Remember, it will look different depending on what you're looking at. I have focused a lot on the 128. And here, once again, you get the layer text. So you have alignment marks here, the text itself, the various layers, and what I could see and you couldn't, the test transistor sitting right there. It's usually a very large one. Yeah, there you go. So that looks pretty interesting. Sorry for just messing around here. I'm trying to find something I can use to show a bit more. I got a question whether it's NPN or PNP. No, it's neither. This is not bipolar, this is NMOS, so it's MOSFETs, where the doping is N-channel, not P-channel. So they used NMOS because it was an easier way for them to use that process. Some of the earliest microchips, MOS style microchips, were PMOS. So the Intel 8008, I think, is PMOS. I'm not entirely certain on that, but I do know some of the earlier chips were all PMOS. This is all NMOS, and I will show one of the reasons why once I find a good transistor to show it with. I wonder if I still have a 128 PLA in a useful condition, because that would be easier. I'm very familiar with that chip. Let's have a look. I think this looked like one. Yeah, what are you? No, this is a 6526. Huh. I would like to be able to say, here's one I prepared earlier. What are you? I have no idea. You're a wrecked PLA. And you're another experiment. So it doesn't seem like I actually have a good PLA. That's just a... What are you? Oh, yeah, this one might work actually. This one is a bit of a unique chip actually. Most of the 74LS chips are TTL, which is a different type of manufacturing technology or design methodology. Commodore at one point decided to make their own logic chips to save money, because they do this full... They always loved this whole full integrations kit that they were doing. So they actually designed their own logic chips instead of buying them, because I assume it was actually cheaper for them to do this. And this one is a MOS 7708. I think that was shown. Yeah, exactly. 7708R0. It didn't really come off on the stream. Oh yeah, that one actually has another useful thing to show. So this is a 74LS257, as you can see now on the screen, implemented using Commodore's NMOS process. Once again, you see the same, the layers set up, you see the designation, you have the test transistor, and here you have layer alignment marks. That's the ones I wanted to show now that I saw them. So let's zoom in a bit more on those. They're a bit gritty, but it actually shows another thing. So these are layer alignment marks. You can actually see these are silver white, so they're metal, and these are doped parts of the substrate. These are going to be polysilicon and substrate, and etc. etc. So it's really matching. These marks are set up to match between different layers, and they use these to align the masks to make sure that everything is just set up, just like when you do a multi-layer PCB. You have to make sure everything matches. That's what these marks are here for. And the thing I wanted to show here is you see this grubby bit of dirt on top of it. That's going to be part of the passivation layer. And the passivation layer is a thin layer of glass that sits on top of the entire IC die. It's called passivation because it's there to keep oxygen out of the chip itself. The epoxy is the epoxy of the packaging is of course very tough, but is not 100% airtight over decades. So it allows a bit of air and water to slowly permeate through it, and to keep that away from the die and to make the dies easier to manage during the manufacturing process. They put the final thing they do is they put a layer of glass on top of the chip called a passivation layer because it passivates the chemical reactions from it. As you can see from this photo, it is glass, and as such it tends to make everything grubby when you try to take photos of it. And you want to remove this glass if at all possible when you set up to take shots of things. I will discuss this also a bit more in a short while. I'm just trying to see if I can find the actual logic implementation on here. I think it's mostly hidden away and split up and separated in a way that it'll be hard to show. Let's see if we can see something here. I basically just wanted to try and show a transistor itself. Yeah, there we go. Zoom in a bit more and see. So these wavy things here, they are transistor. These are power transistors for the output. So it's basically a very large transistor, or you could even think of it as multiple transistors in parallel. And let's see if I can find, yeah, it's kind of hard to really show. I wish I had one of the 128 PLAs because they are very conveniently laid out for me to show things. The only ones I have are kind of busted, really, because I've been doing destructive things to them. That was the MMU, right? Yes, that was the MMU. Let's see if go transistor hunting on this thing. It's a bit grubby, and what I usually do to clean them up a bit is I stick them in an ultrasonic cleaner. It's not exactly a perfect thing to do, but it does the trick for me at least. I'm really just trying to find a nice clean transistor to show. So most of the lines that you see on this screen is just interconnects. Going from one part of the chip to another. There we go. There we go. Found one. Finally. Found a couple of them actually. That's pretty isolated. So let's go all the way in to the cleanest one of them all, which is right here. This is one transistor and a pull-up resistor. So the way these chips are implemented, I'm just reading the questions here. It is certainly possible, for sure, to replicate these using modern chips. I've already done this with one chip. That's why I was trying to find. This was literally the reason I was trying to find a C128 PLA chip. I've documented the process that I did there. This is one of the simplest chip there is to reverse engineer a mask ROM or a PLA chip, because a PLA chip is basically just the same as a ROM in many functional aspects when it comes to reverse engineering it, at least. But it's certainly possible. That said, reversing the logic is only one of the steps that you have to do. You also have to work out a lot of other parameters. So if you look at the PLA, for example, I have the logic equations. There might be a few small revisions due to manual errors in the reading process. That's fine. But I still have to work out the correct timings. The PLA on the 128 is also involved in the DRAM process, so it manages the CAS signal. And DRAM timing, honestly, if I look at most of the custom chips in a C64 or a 128, their primary job is really to keep the DRAMs happy. The timings involved in managing DRAMs, even these really old DRAMs, has to be fairly precise. If you screw up a bit too much on DRAM timings, the machine stops working. And with the PLA on the 128, using that as an example right now, I have the logic correct, but the output signals come about 25 nanoseconds too fast. I can run a 128 with the PLA replaced with a modern programmable logic chip, but it's not very stable right now, and it will only boot about half the times. Slow timings, yes. In some ways it makes it easier. In other ways can even make it a bit harder. The PLA chip is a typical example. If I look at the Commodore 128 MMU, the chip we're looking at right now, I have a clock signal available that I can synchronize things with. That makes it easier. If I have the clock signal, I can also stick that clock into a PLL and generate higher clock frequencies internally in the chip, which I can then use to delay outputs, for example, to simulate output delays. The PLA is a bit unique because it's almost entirely combinatorial logic, e.g. if I have this set of inputs, I will have this set of outputs. There is no state inside of the chip. And as such, there is no clock signal input into that chip. I have no external clock I can reference other signals off. This is not how you build computers and logic today. In pretty much everything is fully clock driven in a modern design. This makes it much harder, so I'm working on ways of delaying these output signals while still sticking within the actual socket of that chip. I don't want to have to run off a wire to pick up a clock signal from somewhere. I will do that if I have to, but I would really prefer not to. So I'm working on ways around that. You can force the synthesis, so the thing that takes your source code and turns it into the connections on the programmable logic chip, into force it through multiple gates to also delay it, but you start really eating away at the amount of gates that you have available. To replicate multiple chips on a newer chip, absolutely. That happens all the time. I mean, in many ways it's even easier because it's actually easier to replicate a full Commodore 64 on a single FPGA in many ways than it is to make FPGA replicas of chips that goes into an actual computer. Because if you replicate everything into one single chip, you can synchronize the timings internally inside of that chip. It makes it actually easier in some ways. You also have other things to worry about, like level I/O voltage. You will not find many things today that runs on 5-volt logic levels. Certainly not programmable chips. You might find a few scarce ones that are 5-volt I/O tolerant, but pretty much nothing outputs 5-volt anymore of any form of size. Even 3.3 volt is slowly starting to go away, so that will become a bit of a problem. Once again, if you replicate the entire thing, that's not going to be a problem for you. You also have not only the timings, you also have things like slew rates to care about. How fast does the 0 change to a 1 and a 1 change to a 0? That's a slew rate, so basically the slope of the voltage translation. Modern chips are really fast. Older chips, results vary, shall we say. You can also run into a lot of fun issues with just simply noise on these old chips. They're very noisy. Modern chips tend to be a bit less noisy. They use CMOS, for example. NMOS is in many ways a bit inferior, shall we say. I'm not going to go into the full details of that. So going back, what I wanted to show is pretty much this thing here. What you end up with, the way that NMOS is designed is, NMOS and PMOS actually, is you use RTL, so resistor transistor logic. So it's the chip internally is just full of pull-ups. In the case of NMOS, you have pull-up resistors and transistors pulling things to ground. That's the way these chips work. And what you can see here, I'm not going to go into the absolute technical details of it. I will probably do a how-to video more organized on this instead of a live stream on these topics, specifically to the Commodore NMOS process, which is the one I know the best. Because you have different types of doping that you can do. You have normal doping and you have depletion mode doping. And it gets a bit complicated, but basically inside an NMOS chip you can, with the same process, largely create really weak transistors, resistors and transistors. So if you look at this really wide part here, you have a doped area sitting here, shaped a bit like a hockey stick, if you will. And this hockey stick is a very common design theme that you will see in at least in Commodore's NMOS processes. The large end here is basically going to be a resistor, and the thin end that goes across this other one is a transistor. So what you have here is a transistor on this connection here that gets shut off on and off with the signal from here. You can see more of them down here. Let's see if I can refocus a bit. The reason it's not focused is, of course, because I haven't leveled the die to the chip. So here you see a bit more things. You have a hockey stick going across. There's another one sitting right here. I'm not really a professional at reading all of this yet. It's work in progress. But once again, this here is for sure a transistor. This little thin line going perpendicular to another line, that's guaranteed to be a transistor. This is just a normal transit connection. You can also find, you can create capacitors very badly using this process as well. They're gonna be absolutely horrible capacitors, but you can make them. You can also see on this picture here that the metal layer tends to really obfuscate a lot of things beneath it. You can't see through the metal layer. It's not too horrible on these old Commodore processes. Quite often you don't end up having to take things apart just to see what's going on under them. But sometimes in slightly newer things, certainly a few of the Apple things that I was doing, you have to. Here's an example of this. There's a lot of action going on under here. You can see the vias. And what you can also see is indentations in the metal layer, right? When I say layers, they're not going to be nice, flat, even layers sitting in layers above each other. It's actually going to be a 3D part because different parts have different layers there. So when they sputter the metal layer on top, for example, it's going to shape to the valleys and mountains, if you will, of the layers below. So it's really a 3D type setup. And you can actually see the profiles of this here. So you can get a bit of an understanding of what's going on underneath these big metal surfaces. But you won't know for sure unless you remove the metal. And this is where it starts getting a bit horrible. Because, remember I talked earlier about the passivation layer? In order to remove the metal, you have to get rid of the passivation layer. The passivation layer is silicon dioxide, normal glass. Glass is popular because it doesn't react with a lot of things. That's one of the things that glass is very, very good at, especially acids. And there is one acid, and I think it's, in my research, it's the only feasible way of doing this, and that's controllable. I'm sure there are other ways. Somebody will know better than me. what you end up with is hydrofluoric acid. And if you thought that fuming red nitric acid is bad stuff, hydrofluoric acid is the stuff of nightmare, right? It is the stuff where I prefer not being in the same block as it. I really don't want to be anywhere close to it. Unfortunately, I have to. Obviously, I can't just go out on the supermarket and buy concentrated hydrofluoric acid for obvious reasons. Yeah, exactly. Hydrofluoric is horrendous stuff. It's been called the piss of Satan more than once. Most chemists will know that as soon as you use the word fluoride or fluoric, it's time to run, right? So what I use is, I'm gonna go fetch it. I have a hunch my microphone might turn off when I do this, but I'll be right back. So, no, okay, it keeps on going. So, what I tend to do, I hope I'm back now. So, what I tend to do, and I can't remember where I found this. Let's go back to the camera again. This is what I use. From the arts and crafts department of the hobby store. I was genuinely shocked when I found this stuff. So, let's see if we can find... it says, danger causes burns which may not be immediately painful or visible. May cause permanent damage to skin, eyes, and respiratory tract. And that is true. The big problem with hydrofluoric acid, I'm not going to go into all of the horrendous details of it. The big problem with hydrofluoric acid is that it loves calcium. So if you get concentrated hydrofluoric acid onto your skin, it's going to go straight for your skin and start eating away your bones. Right? And there isn't really many ways of stopping it. So this one, what it basically says is contains ammonium and sodium bifluorides. And what that basically means is once you expose this to, you put this on stuff, it's going to start to devolve, I don't know the exact chemical reactions, into about 3% hydrofluoric acid. That's what it will do. And you notice I'm wearing gloves. I'm wearing gloves just to handle the bottle. Remember, this is sold to artsy-fartsy ladies that want to put some cloudy etching on glass. It scares the crap out of me. So that's what I use. The gloves I'm wearing, normally you would use nitrile gloves. Do not do that with hydrofluoric acid. It will burn. So, I'm not going to show that process right now. Suffice to say, I'm wearing a gas mask. I have my gloves. I use a lot of protection to do this. But it works. And with the really low concentration of HF that you have, you get a really slow process. I don't have to heat it. I can just let it sit. And I like having the slow process of it. Because the other thing with hydrofluoric acid is it will eat the passivation layer. It will also eat the aluminium layer. And then it will eat the other glass layers inside of the ship. So if I don't really aggressively time and control how long I have it on there, it will literally melt away everything except the substrate on here. The polysilicon will also be left sitting, But as soon as I do anything to touch it to get rid of the little bits of remaining gloss, etc., or heck, even flush it with just the acetone I use to get rid of the crap, it will just flow away because it's not anchored to anything. Hydrofluoric acid, I tend to wash it off with acetone, which is also not a very nice liquid. Dilute it quite a bit in acetone, and then I use the chemist's happy Mr. Baking Soda. Which is an alkaline, so it helps really just neutralize most of the acidity. I haven't looked into the exact chemicals, but it seems to be working fine for me at least. I probably should look that up. I do have quite a lot of other things as well. So acetone is very nice. Acetone is a very nice cleaning detergent for a lot of this crap, for most of these things. You don't want to put acetone on plastic or anything like this, obviously. But it's very useful for this. So I tend to clean off the crud with acetone. Let me just plug it in. There we are, sorry about that. So I use acetone to clean off the acids that I use. It's not just HF. I have a few others that I tend to use as well. I'm playing around with phosphoric acid now to work on the aluminium layers a bit more controlled. So acetone to rinse it off. I then remove the acetone using deionized water, so distilled water, and then I chase the water off using IPA. IPA is everybody's best friend. Neutralize and dilute, and then take it off to the recycling center. They tend to look at me a bit weird when I show up. So that's all of the acid type stuff, and I can, if I flip back to microscope stage, I can actually show some of the results I have. So fully zoomed out. It's a bit dirty because it's been lying around for a bit. But this is basically what remains of a Commodore 128 PLA when everything else has been removed. This is the pure substrate of the PLA chip. Let's see. So a PLA, as said, is largely a form of a ROM. It has two major structures. There's a AND structure and an OR structure. So inputs go into the AND. Intermediary AND product goes vertically up to the OR structure, and the OR structure goes to the output. That's how these work. And here you can actually see what remains. This is the substrate layer. So when everything else is washed off, what you end up with in the end is substrate and doped areas. And in this case, it was incredibly useful. Sorry about that. So if I move in, a bit too far, if I actually zoom in a bit on this, yep, what you end up seeing is the substrate. So in this case, the substrate is the mask they used to program the PLA chip itself. So these little winglets here are transistors, the doped areas of transistors doing the connections. And by just stripping everything off, I could easily read out the contents of this. It's gotten a bit dirty and grubby because it's been a long time since I stuck this in a microscope. I'm sure if I stuck it in a ultrasonic cleaner, it will clean up nice. I do have another PLA chip, I think this is. Yep. And this is one where I was working on I was trying to delayer the chip to just remove the passivation layer and the metal layer. I wanted to leave everything else in place, so the polysilicon layer. Results were less than impressive, shall we say. It ate away too much of the various bits. So you can really see how the metal started stripping off. So this is a long metal wire that's just bent down from here, and there is bits of it flying everywhere, etc. So that didn't turn out too well. It's a process in learning. That's why I'm always very thankful for donations of broken chips. It helps me have resources to work on to perfect my processes and how I do these things. Now with my processes all discussed and talked about, what we're gonna do now is... where did I put the thing I was working on? Oh yeah, I should finish with that as well. What I tend to do, or have done quite a lot so far, is I mount... Sorry about the mess, I'm new to this whole streaming thing. I tend to mount the dies on microscope slides. And that's where I've made pretty much the only major chemical boo-boo I've managed to pull off so far. I will go fetch a slide and show. So, here's a normal blank slide. We've all used them at one point in our life or not. And if I look at a die, so let's see what do I have here. No, not that one. Yeah, let's do that one. So, I'll just shake it out. I'm not gonna do this now. I will leave this one as is for now. I would usually just put the die on here, like this. This is a Macintosh SE BBU chip that I prepared earlier. I'll put that in the microscope for now. But what I usually do to mount them on the die is I use a glue. Of course I do. A super glue, like most of us. This glue is, as you can probably guess, it says right here, cyanoacrylate, which is a fairly decent glue for these type of jobs. It doesn't really react with a lot of things, and gluing the die to a microscope slide helps me work with these acids in a much safer manner. Instead of fiddling about with a couple of square millimeters of silicon die and trying to put stuff on it, I can just work in relative distance away from the die by just holding the slide and using Q-tips and whatever to do the thing on the die itself. Back to the major boo-boo that I made is I thought the glue took a bit too long to dry, so I tried to help it along using my hot air rework station. Do not do this. I did some read up afterwards, and yeah, don't do that. If you heat cyanoacrylate glue above, I think it's 120 degrees, you get hydrogen cyanide, e.g. gas chamber type stuff. So yeah, don't do that. Don't use super glue if you're gonna heat it. Useful chips. Right now, pretty much anything Commodore or Apple, and I'm talking 80s, 90s machines. So Mac SE, Mac 2s, Commodore chips of all variants, because Commodore and CSG never really changed the process. They used NMOS up until the end. That is broken. They don't have to work. I don't care if they died due to corrosion issues. I don't really care if they died due to static electricity, whatever. It's all fine with me. So as I said, I got this really nice bag from Rob Taylor, and I've been using this already quite a bit to practice the decapsulation and also to work on the timings that I need to remove passivation layer. And I'm currently trying to work on the getting rid of hopefully the metal layer as well. So I'm gonna flip on back to the microscope and we can go exploring. Now this is not a Commodore chip. Once again, I have not cleaned this die in any way, form or shape. It's right out of the chip of the package. We'll go to smallest magnification and have a look at it. So as said, what I usually try to do first is find some form of identification on it. So normally if I want to image the die, I have to make sure that it's not only level but also aligned with the motion of the table. I don't want to have skew to deal with when I take the images. So there we go. And here's the chip identification. So as said, this is a BBU chip from a Mac SE. Memory chips aren't really that interesting, to be honest. DRAM is DRAM. There's not exactly much to reverse engineer in them. They're usually not done, to my knowledge, in the same processes either. They're done slightly differently to most other chips. That said, I don't mind at all, of course. Let's see. So once I've looked at the ship identification, what I tend to do is just zoom out and get a clearer type of picture of what's going on with a chip. And in this case, I said this is a BBU chip from a Mac SE. What we can see already, I think I have a slight disconnect in focus between the binocular and the camera, but that's fine. What I can see at a first glance is you have this repeating structure at each bonding pad. So that means there's basically a generic I/O driver for the I/O pins. It depends on the purpose of the reversing. In this case, with the Mac SE chips, I've worked with or discussed it with Kai Robinson. So he became aware of what I was doing with the imaging when I was working on my Commodore 128 stuff on Discord. And he got interested, of course, because he's also interested in reverse engineering the custom chips of the Mac SE. So I said I'm not exactly a huge Apple man. I haven't really ever had any personal relations with I've never actually owned an Apple II, for example. I never really used an Apple II. I was never really big on Macintosh. Back in those days, I was an Amiga zealot. So I don't really have that big of a relation with Apple, but I promised him that I would at least help him image the chips. I also don't mind helping out a bit, looking at the structures a bit, and I said I'm slowly starting to gear up my lab a bit more so I can start making more content videos on YouTube on what I'm doing and how I'm doing, and also a bit of information on how these chips are actually designed and laid out, because I found it the hardest part for me of this was finding information. I ended up buying textbooks, university textbooks from the 70s to get a better understanding of the NMOS processes. So going back to this chip here, we can see a couple of things already. Let's just move along a bit. So we have the bonding pins going to repeating structures like this, and I can tell this part here, for example, just at a glance, you see the wavy lines. That's going to be a power transistor for the output. I'm sure these are bi-directional as well. So you will have pins, wires connecting into these structures, which then go to these pins. So these are largely just going to be amplifiers. Internal signal gets amplified so that it can actually run external chips. That's basically what these structures are going to do. There might be some extra logic in there. Especially if I look at it quickly, I can see there are multiple pins. If you look at the bottom here, there are multiple pins going into these structures. That might be to these extra pins might be to have an output enable, it might be to tri-state the outputs, etc. There can be all sorts of things, but what I can usually tell already from this is if I reverse engineer one of these I/O segments, we're gonna be done. Chip designers like to copy and paste things. So this repeating structure, you reverse one, you will know how it works. The other part that we see on this here is basically this sea of gates. So what I will do is I will zoom in a bit more on this, because this is interesting to me as well. See if we can figure out a bit closer what's going on here. And yep. I have not really looked at this ship all that much. I've just put it in the microscope to make sure that the ship came out okay-ish. And beyond that, I haven't really looked at it. So, go to 200 times. Yeah, there we go. So, this is basically standardized sets of gates. I need to have a closer look at one of these gate structures that you have here to understand what each of them are doing. But as you can see, they're all standardized and set up in a matrix. And then you have interconnects. So there's looks to be two metal layers that is then used to interconnect all of these gates to do various things. So I can zoom in a bit more. On one of these, and let's have a look and see if we can figure out what's going on a bit more. Take the bottom one here, for example. This is a bit more modern of a process compared to Commodore's. It has finer features. I don't think is nanometers just yet, is micrometers, but it's for sure a bit finer. I dare not say what process it is, but I would not be surprised if this is CMOS and not NMOS. I didn't check what's the date code on that chip. Come on, you stupid thing. That's a 1986 ship. But it was manufactured in 1990. Week 23 of 1990. So it's about 10 years newer than the Commodore stuff. And I would not be surprised if this is CMOS. I can't tell straight away. There's also something... Dual metal layers is something Commodore never did. So you can see it here. You have two layers of metal with interconnects between them. You can tell from the color, basically. There's a doped area under each. You can see a square barely in the background there. And you have polysilicon legs going through. So these are going to be pretty much standardized gates, which are then interconnected between each other. There you go. To form the logic that you want. So this one is probably something, if you image this good, so get a nice clean picture, probably remove the passivation layer and image it. You probably don't need more than 100 or 200 times resolution for it. This is the type of thing you can probably stick into software such as dgate to reverse engineer the actual logic. So dgate is a software that will recognize these type of standardized gates and do image matching in essence. I don't know if they've gone full machine learning yet, but it certainly does image matching and some form of bit of intelligence, etc., to figure out if this is a gate that a D-flop for a flip-flop, for example, or a JK gate, or etc. And then you can look at the interconnects to figure out how these things are connected. So I will work on capturing this in some decent resolution for sure. So shouldn't be rocket science. And it's just basically one huge blob of these type of gates. Lots and lots of these gates. So it's gonna be a almost standardized chip. It's like programmable logic, except you program it with designer software and have them manufactured that way. It's not a. It's kind of halfway between programmable logic and a full ASIC, if you will. The ULA chips in the spectrums are done in pretty much this manner as well, as far as I understand it. It's kind of a standardized gates with interconnects set up, and you program it using masks. In this case, it's the metal layers doing the interconnects that will do the programming of this. I think. I could be barking up the wrong tree, of course. Is it possible to fabricate these things? No, not from this type of process. In theory, possible, but the thing is, you will not get all the information out of the chip by just imaging it this way. As I mentioned when I was talking earlier about, you have depletion doped areas. With a picture like this, unless there is an additional chemical process I'm not aware of, you will not really see the difference in a photo between a doped area and a depletion doped area, if I'm talking NMOS, for example. I can recognize the depletion doped areas due to the structure of the other layers, but I can't tell that it is depletion doped. In fact, I can show that on the on that PLA chip I showed earlier. Where I was down to the substrate. Yeah, this one. Exactly. So if I zoom all the way in, let's zoom out. I'm gonna go to. I have a nice clean output stage. Yes, I do. Good. So this is a chip I am, as I said, intimately familiar with. So even when it's disassembled like this and really scraped down to the bare minimums, I can actually tell what is what. Let's see how deep we need to go. No, we can go full blown. Here you go. It can be a bit hard to see, but these are doped areas, and you can see the little marked areas inside of these to some degree. So these are where transistors have been located, these little lines here, and they are doped areas, but you can't really tell. So this one here, for example, is actually a resistor. It's been connected to a metal layer right here, and this doped area here is actually depletion doped to make a resistor, not a transistor. You can't see that. It looks the same as the other bits. So you can't get all the information. I'm sure there is some chemical process you can use to redope the areas and have it absorb different depending on which doping you have in that particular area. I've not dug into it because it's not largely relevant for the work I'm trying to do. Yes, you can lap chips. Some people do. The problem is, of course, the thickness of the layers. Once again, as I mentioned earlier, it's not going to be nice flat discs stacked on top of each other. It's more like a 3D structure. Hang on, I think I can show this. No, not that one. That's the completely wrong book. Let me just find. That's the book I was looking for, at least. I will show this book later. It's one I learned a lot of things out of. It has some really interesting parts in it. It's called Introduction to VLSI Systems. It's a textbook from the late 70s. And many Commodore chip people have said that this is the book they had on their desk when they were laying out the chips, and also to develop the actual chip manufacturing process. No, those pictures are not in here, as far as I can tell. No, they're not. Okay. I'm just gonna go fetch that book. Back to camera. So this is basically the book I was talking about. It's Introduction to VLSI Systems by Carver Mead and Lynn Conway. It basically contains most of the information you need to manufacture NMOS chips. It doesn't hold a full process with all the various chemicals, etc. The chemicals used to manufacture chips is proper nasty stuff, and I'm sure compared to a few of those things they use, hydrofluoric acid is nice things. As scary as that sounds. And in here I should have, I'm looking for a specific part, sorry about the delay. So around here, yeah, there you go. That's the page I was looking for. So that's basically what happens with a process. So you have you add a glass layer, and you do the ion implantation, which will then be masked off by this glass layer, of course. You do the polysilicon layer, but remember, many of the glass layers are still there, right? And you add the diffusion regions. You place the contact cuts, which is holes in the glass, and then you pattern the metal layer. But this is the picture I wanted to show. This is basically the type of 3D structure that you end up with. So you will have the substrate at the bottom, which is flat. You will have diffusion areas. You will have polysilicon. You will have more glass areas. You will have metal layers that are all conforming to the glass and polysilicon and everything else that's on here. So it really gets into this interesting 3D type structure. If you start lapping on this, you might not get the expected result because this is a 3D structure like this. Also remember, the thicknesses of these layers is incredibly thin. Incredibly thin. I wouldn't be surprised if some of the sputtered layers are basically I wouldn't be surprised if they even measure it in Ångström. So it's this book I can recommend. It's really good reading, especially for NMOS processes. A lot of information that you can find online today is largely focusing on CMOS. Yes, vapor deposition, exactly. They call it sputtering, but they sputter to do vapor deposition. That's the word I was looking for. Thank you. So it's gonna be really thin stuff. Yeah, I was talking about the book. Yes, this book has been really useful for me to start really understanding the NMOS stuff. You can probably find this one online in PDF form if you dig deep enough. I decided to buy it because I considered it to be one of those nice things to have in the bookshelf, really. Most of the information I found online today contains a bit about PMOS and a bit about NMOS, and then they go straight to CMOS, which is what everything is done today. The reason behind it is basically the major reason for the power draw and the heat generation in an old Commodore ship, for example, is because it's an NMOS process. These pull-up resistors inside the ship will always be active. They will consume a bit of power, they will generate heat. And NMOS uses pull-up resistors, PMOS uses pull-down resistors. They're incredibly weak, these pull-downs. So what they quickly learned, once the processes they use got a bit better, is if I combine a PMOS for a pull-down and an NMOS for a pull-up, I get complementary MOS, so I have P and N. And that basically balances out. If you do it the right way, it balances out and you don't really get a idle power consumption. And it's just generally a much better process. But when working with these really old ships, NMOS is easy to understand. And you get into this RTL type logic. In fact, hang on. Another one I might recommend. It has a bit of detail. Is the seminal white paper as it regards to the Commodore 64 PLA. Which is this PDF file that I linked here. This is the document when it comes to how the C64 PLA works. And if you scroll down a bit, he actually goes through the decapping. He's using a different way. I think he was using resins to remove the plastic. Yeah, rosin, exactly. Cooked in rosin 2 times for several hours. So rosin is, pine rosin is also a way of doing it. But he actually goes through a lot of this reverse engineering as well. He shows die shots, process sizes, a bit about how the PLA works, the ESD protection, and the most interesting part for me is he shows images of the reverse engineering that they did. Hang on. So if I do... no, not bookmarks, I want that one. And I can drag this one over here. I flip to here, right? So he goes through all of this and you can see the die shot that he has here. He then shows his reverse engineering result. So here you can basically see the various layers. So blue would be metal, green would be diffused areas, and red would be polysilicon. You can also see a bit of yellow here. And those are the specific areas that I was talking about. That's basically the depletion mode doped areas. So T4 here, for example, is going to be a resistor. It's not actually a T8 here is another good example. It's not actually a transistor, it's a resistor. So it's a pull-up resistor. And then he basically goes to show the result of that reverse engineering to some degree. He doesn't go into the full details of how it's all set up. But you can actually see the type of logic that you end up with. So that one is also worth a good read if you're interested in these type of things. You end up basically digging information from all sorts of corners to get an understanding of how things hang together. And that's one of the things I want to do. I'm gonna try and do on the YouTube channel is go through these type of things and really start documenting in videos the full reverse engineering process, how I go through let's say for example the Commodore 128 PLA output stage and figure out what it actually does from looking at the die shots. So moving on. The final thing I was gonna try and do today is this little fella here. I think that's the one. Yes. There you go. So this is a slightly smaller die. Go back to there. This one back to here. There we go. It depends on the chip design more than the process. Sure, you get more tolerance just due to it being higher voltages and large voltage swings. But on the counter side, these chips are also a lot more noisy in general. So this one is, if I don't remember completely wrong, oh come on kitty, I'm trying to stream here. Yes. This is an ADB chip from a Mac SE. And the thing I wanted to show on this one is probably the easiest type of reverse engineering that you can do on these older things. And it's not just older things. This is almost equally valid for modern things as well. So the first thing we see is, of course, this huge rectangular regular structure. Come on, kitty. Jump down. I need a door to my lab. Hey. So this huge... Yes, that's a microscope, kitty. Come on. Sorry about that. So this structure here is basically going to be a ROM of some kind. What you will often find inside of chips is, instead of doing, at least in the older ones, instead of doing structures of transistors, etc., they will quite often just use a PLA, for example, to implement logic. Because a PLA is a thing that's easy to lay out. So don't underestimate. One of the things I like with these older chips, like the Commodore ones, is the amount of handicraft involved. These were laid out by hand. They might have had some rudimentary CAD systems, but the actual designs were handmade. They're like artworks, almost. It makes it a bit harder to reverse engineer in many ways, because they will use every single trick that they've learned to minimize the transistor counts and make a smaller die. If you compare to the BBU chip we were looking at earlier, there's a lot of empty space on it. because it's just a standardized structure that they would adapt to their requirements. It's probably software that generates all of those interconnects and lays out the thing. They just describe it with a hardware description language and they get the output that they want. And there you go. The old Commodore chips, I mean, those were handmade to a much larger degree. So, going back, the structure we're looking at here is a ROM. So this chip I know, because I've been told, is a PAL 16 CR8. If it was HR. It's basically a normal PAL 16 VA chip, but it's programmed using a mask ROM instead of being programmable. So it's basically pre-configured at factory when they made the chip, and that's it, done. So I'm just gonna pop over to some area around here and see if I can get a focused shot on this. One of these areas. I'm at 20, so. This one is actually suffering quite a bit from my big problem with using gluing the dies to a microscope slide. It's hard to get them even with the slide. They tend to float a bit on the glue, and I need to come up with a better way of doing this. I need to mount it on something so I can work with the acids on them. In any case, but this one basically shows what I'm trying to show anyways. Let's see if I can find a better area on here. Let's move around a bit. Yeah, the focus is just horrendous due to the tilt of the die. And that is absolutely atrocious. For pure exploration, it's usually a lot faster to just use move the table by hand. However, I can't do that due to my modifications, so I end up having to go through the bit of pain to use the jog controls. There we go. So that's the point I was trying to get to. This one has a 512 byte mask ROM, and you can actually see the structures here. It's really terrible. I think I have a better shot stored somewhere, because I don't want to go through the process of trying to level this die right now. That would just be awkward. Just going through my stored pictures here. Yes, as an example of what I was discussing earlier, this is a clear shot of the output stage of a C128 PLA. And here you can really see the various transistors and interconnects and everything else. This is literally the image I used to reverse engineer this output stage. So this is probably what I will use to demonstrate what I did when as a video to show how I reverse engineered this stage here. So I should have a better picture of There you go. This is a slightly clearer picture. The white balance is off. But this is a clearer picture of the ROM section of this exact ADB chip. And if you start looking at it, if I zoom in a bit, you can actually start seeing differences as you move along. So if I count from the top here, for example, not connected, 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 not connected, 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 not connected, connected. And if you count, if I take these, for example, have wider connections, the first ones coming from the side. And if I go down, the bottom one will be the same. It will be connected on the other side, I guess. And if you start counting, you have 1, 2, 3, 4, 5, 6, 7, 8 in each of these sections. So each line here will represent 1 byte of ROM. And what you have is basically the brown here is the substrate. Green is going to be polysilicon. The yellow stuff is the metal layer. And that's pretty much going to be it, really. So each interconnect here represents 1 bit. So each line going through the block is going to be 1 byte. Each interconnect of the center section, the 8 center connections here, is going to be 1 bit of that byte. And you can clearly see the difference between a 0 and a 1. So what you will end up doing to read out the contents of this ROM here, for example, is you will go through and you will mark these up. I can do a bit of drawing on here. So this one is connected, this one is connected, this one is connected, this one is connected, and this one is connected. So this is going to be either 0, 1, 1, 0, 1, 1, 0, 1, or the other way around. Or alternatively, it might be that these that are connected could be a 0, so they're inverted. In which case this is going to be a 1, 0, 0, 1, 0, 0, 1, 0. But there aren't really many ways you can parse this data anyways. It's fairly clear cut. It's just a matter of imaging it properly and either reading it out manually or sticking it into a piece of software like ROMPAR, for example. ROMPAR is a piece of open source software that's made specifically to extract data from these type of mask ROM images. And my focus right now is going to be in with the mounting of this ADB chip on the slide. I think I'm gonna have a really hard time. So my hope is that Kai has a few ADB chips, broken or not, that he can send that I can rip apart and really work on to make sure I have a proper set of images for him. So, yeah, this first shot was a fairly quick and easy shot that I made as I just popped the die open. Sometimes you get lucky. What you can do, I think one of the best sets I've managed to do so far is, I'm just gonna show, no, come on, arg. I'm horrible at this stuff. There we go. This is probably the best total set of images that I've managed to do as far as I can done so far. So this is basically a zoomable image map. It's not perfect. I still have some blurry areas here and there. But this one ended up being pretty good in general. So this is basically a 6526 chip from a Commodore 128A or even a Commodore 64, it doesn't really matter. And it will literally marked 6526A on the outside of the chip. And once again, once you crack it open, it will actually say 8521. So the way that Commodore worked, this is basically the 8, the first number, was their internal process ID. So this would have been what they called HMOS2, which is a certain process size of NMOS. Because remember, they never did anything but NMOS. I can't remember the feature size of this one. And it's similar to the Amiga 8520. So the CIA chip in the Amigas was the 8520. This is the 8521, and the only difference between this one and the 8520 is the way that the time of day clock actually works. This one will actually use BCD representation of real time. So it uses BCD encoding is hexadecimal without using the upper character. So you encode decimal using the hexadecimal letters. 4 bits per digit in essence. 0 to 9. So this one basically, if you read the time of day registers, you will get BCD represented clock out of it. Whereas the Amiga chip counts seconds since midnight, like a reasonable computer would do. Of course, in the Amiga, having the 68,000 do the conversion is so fast that you're not going to notice it. Whereas having it BCD encoded in the C64 with its much lower CPU that actually supports BCD straight up makes it a lot faster to use the time of day clock in BASIC, for example. So it's all give and take. One of the reasons I'm doing this one is I wanted to also capture an 8520 and see how large of a difference there is between the two. Yeah, this shot turned out pretty good actually, and as you zoom in, this is, I think it was taken at 200x. You can actually start really seeing the details. That said, this is only half the image. What I would like to have is another set of images taken at the same resolution with the metal removed. And preferably even a third one with just the substrate and diffusion layers. It might be overkill, but for me that would be a nice way of documenting these old chips, and that's what I'm trying to achieve. Here you can see the same type of structures. Here you have a pull-up resistor connected to, this is going to be VCC. Going across to transistors here and here. And there are many ways that you can build logic using just resistors and transistors. So pull-ups and pull-downs. So this one I would say is probably gonna be reversible from these images, this set of images alone. I don't want to swear on it, but I'm guessing that's gonna be the case. That said, the 6526, 8520 is pretty well understood. I think I know of at least 3 projects ongoing at this point to replicate these chips. I think that's pretty much what I had for this stream, unless there is anybody having questions. Hello, other kitty. So I said my current focus is pretty much going to be try to image the BBU chip and image the ADB chip. I still need to improve my processes a bit. I need to come up with a way of mounting these dies so I get them fairly level from factory, but aside from that, no, it's pretty good already. Come on, kitty. Go pay the kitty tax. You know you want to. There you go. It makes it extra challenging to work when you don't have a door to keep the kitties out. Oh yeah, no, for newer chips, once you start going down in feature size, remember this is Commodore NMOS from a late 70s process. These things are huge. I can't remember the exact process size. I can't remember the process sizes that Commodore went down to. Trying to look it up. Comparatively, I mean the feature sizes on these is just gonna be absolutely gargantuan compared to most of the other things that you think of today. Yeah, the 6502 was built with 8 micrometer NMOS technology, and that's pretty much the 8521 here is gonna be slightly smaller. I don't think it will be more than, say, it's still gonna be micrometer. It's not gonna be nanometers. It's micrometers for sure. So once again, if you start looking at the smaller chips, I mean, I know of people that have sweep electron microscopes at home to work on these type of stuff. You can actually see there's still quite a lot of people doing reverse engineering of ICs, either to replicate a chip or to do security research. There's quite a lot of people in the security industry working on these type of things to basically dig out content from ROMs on smart cards and these type of things. And some of the processes and technologies that they do is they get some pretty funky stuff. There's only so far you can get with a normal microscope, after all. And you will also start finding more and more on modern chips. They will put protection layers in there, so you will have thick metal layers on top of really thin feature layers. So if you try to get rid of the metal grid, you will destroy parts of the feature layer as well. And the thick metal layer is just going to be there to protect the features themselves. And so on. There's a lot of things going on there. So it's gotten a lot more complicated. These old machines here, they're quite nice and easy to work with in comparison. There's still a lot to learn when you're doing it, of course. That's an interesting structure. This looks like capacitors. What else? There was something else I was thinking about. Yes, and there are some, frankly, almost crazy people on YouTube. And if you're interested in this type of stuff, one person I would really recommend following is Sam Salouf, who is one out of two people I know of that has manufactured IC circuits at home. The other one being Jerry Ellsworth. No, I mean, you can see replicating as in making fakes. They will look at a ship, reverse engineer the schematics of the ship, and then making their own design or just manufacturing according to that schematic, but with their own process. They're not going to replicate the exact chip layout as is, because that's going to be very, very hard to do, and it's usually not worth it. They will reverse engineer it so that they understand how the chip works, and then make their own clone of it. There's also been known examples of fabs modifying chips to inject features or remove features. There's a lot of funky stuff going on that you can do with this. Once you have the lid off a chip like this, you can even influence it because of how small these transistors are. You can even influence them by using light. This is known to work. There's laser fuzzing, where you shoot a laser at a transistor to twiddle a bit, for example. You have micro-probing stations, where you can open a ship like this and attach probes to a metal line like this, for example, to sniff the data going across it in a working chip. Or inject data if you want. So I said it's a whole field of just craziness, really. Sam Salouf, his YouTube channel, I can strongly recommend it. He has a lot of videos on how he actually manufactures chips, the machines he's using. And it's just crazy stuff, really. I mean, he's making chips that's on level with what you would do in the late 60s, early 70s, probably. But even so, it's just crazy seeing somebody doing it at home. Trying to develop his own photolithography machines, etc., etc. So that one I can strongly recommend. And I said, combining chips, I mean, there is no limits inherent in that. You can combine chips as you go. That's not a problem. We have the typical example of this in retro computing is, of course, FPGA implementations of computers. So if you look at something like the Ultimate 64 from Gideon, that is not a C64 emulator, it's a C64 implementation. So it's a full Commodore 64 implemented inside of a modern programmable logic chip, specifically an FPGA. That means it's not actually emulating the VIC-2 chip, it has an actual VIC-2 chip functionality inside of it. Then you basically, because a modern FPGA is so large that you can put so much stuff in there. I mean, if you look at it, a VIC-2 has something around 4,000 transistors inside of it. A 6502 CPU is about the same amount of transistors. Transistors, not gates, right? If I look at some of the smaller FPGAs that I can buy today, and I'm talking really small ones like the Lattice ICE 40 series, I can get one of the smaller lattice IS-40s is a 1K lookup table chip. So there's 1,000 lookup tables inside of that chip, and a lookup table is, or logic elements rather, you would say, but it's basically a fairly small bit of logic that you can make do a lot of things, and that's as small as you can get in FPGA. If I remember, I can't remember what he has in the Ultimate 64, but I think it's about a 500K LUT chip. So it's 500,000 of these little lookup tables or logic elements. And that's not even the end of FPGAs. They just keep on growing and growing and growing. So there are chips with just, as an example, many modern video chips, so GPUs, NVIDIA and AMD GPUs, Radeons, etc. When they develop them, they run them inside of huge FPGAs to test the validation, because you use the same language to program an FPGA as you do to implement an ASIC. Because it's not really a full ASIC, it's kind of halfway in between. So there are actually FPGAs, huge FPGAs, they cost hundreds of thousands each, these chips, that is capable of basically emulating or implementing a GPU very slowly. But it allows you to basically do a full feature test of the functionality of everything without having to run a full mask cycle. Because manufacturing a chip, doing a tape out and getting it manufactured is not going to be cheap. It's not like back in the Commodore days where it didn't really cost them all that much to do so. Commodore was almost unique in that way. It's also how you end up with a lot of really weird designs at times. One of my favorite features of the Commodore 128 is how the keyboard is connected to 4 separate chips inside the computer. It goes to a CIA for the main keyboard matrix. The 4080 column connection goes to the MMU. The caps lock key is connected to one of the ROM chips. The restore button is connected through a circuit to the NMI stuff. The numeric keypad is connected on the video chip. And there's also direct connections from the keyboard to the CPU. I mean, it's just crazy. There are reasons behind why it's set up that way. And they're more related to what Commodore could do process-wise and what they could not do, and what was cheapest for them. So, at that point, the largest CPU or chip packaging they could do was 48-pin DIP. They didn't have machinery to do PLCC chips, so the largest thing they could do cost-effective was a 48-pin DIP chip. And when they needed to connect the extra matrix lines of the extended keyboard of the 128, because the 128 had to be completely C64 compatible, and the major keyboard matrix is the same, identical as on the C64, so it's connected on the CIA. And to connect the numeric keypad, the extra cursor keys, and all of the other bits, they had spare pins on the video chip, so they stuck it in the video chip. Just as crazy as that, yes. And they could also do a lot of this because the system designers were sitting pretty much next doors to the chip designers who had direct access to the fabs. I mean, they could literally make a chip design and have chips in their hands the next week. As crazy as that sounds nowadays. So that was a really unique situation for Commodore. Apple is kind of getting to that point. but they're not having their entire fab inside. They're doing the chip designs internally, but they're not fabricating the chips themselves. Nobody does nowadays. Even Intel have started outsourcing their manufacturing. They still have their own fabs, but they've started to outsource some of their chips. AMD sold their chip fabs to, or split them off into a separate company. So if you ever see Global Foundries as a company name, that's actually the old part of AMD that was making the actual chips, split off into a separate company. You didn't really need that many interrupts. It was just a timer interrupt that would trigger. I think it was on the VSync, or if it was on a timer itself, I can't remember. Which would then scan the keyboard and then read the VIC chip to scan the extra keys, etc. Some of the more specific keys, like the restore key, is actually hardwired to the non-maskable interrupt. The 4080 column key is hardwired to the MMU. You can read it in a register in the MMU. Once again, I think I don't know why they connected it there, to be honest. And the ASCII, the caps lock key, as it would be on a US machine, is... I can't remember where that one is connected, actually. I think that one goes to the CPU. Yes, the caps lock key is actually connected on the CPU. So there you would basically read from address 0 to get the status of those pins. So yeah, it's a bit of a mess, and it's one of those unique Commodore messes. Yeah, home fabbing. I don't think that will happen anytime soon. If you look at Sam Salouf's channel, you will start realizing that he's dealing with a lot of these chemicals that you really don't want to have in the same city block as yourself. Hydrofluoric just being one of them. They use hydrofluoric acid in modern chip manufacturing to wash things, for example, to wash off photoresists and these type of things. So it's an incredibly dirty business. Of course, nowadays they have to recycle and reduce and reuse. But a typical example, some Commodore's ship fabrication plant, the old Moss Technology building, was basically on the US Environment Protection Agency's super list of dirty sites that needed to be cleaned up, because there was so much crazy chemicals that had just leaked into the ground around there. I think there's a video from I think it's Bill Hurd, where he goes to visit that old plant because he used to work in that building for a short time, and he made the mistake the first time he was there to park on the wrong side of the building, and ended up downwind from one of the exhausts, and the paintwork on his car was never the same again. Yeah, Superfund, that's the one, yeah. So, it's just insanity. So, yeah, I think that's what I had for today, to be honest. Actually, most of the chip manufacturing, China is rapidly building up their processes and fabs. However, most chip manufacturing today, I would argue that the largest foundry by far is TSMC, Taiwan Semiconductor Manufacturing Company. TSMC is by far the largest in the world. Samsung is growing quickly in Korea to build fab plants. They both have fabs in a couple of US sites. There's a few in Europe as well, I think. But for sure, TSMC is by far the largest. There are other choke points as well. The largest manufacturer of one of the most critical machines when you make a chip is the photolithography machine. So basically the thing that takes your design and images it onto the chip. So it takes your design, shrinks it down, and puts it on the chip into photoresists, which you then use to etch things. This is probably one of the largest or most important companies in the computer world that nobody ever heard about. It's a Dutch company called ASML. And they do absolutely crazy things. They're right at the leading edge of physics, even. They build lasers that are just absolutely insane. Because they have to have an exact wavelength. I think in some of their machines they even vaporize metals to use the droplets suspended in vacuum as lenses. So they fire the laser through these things to use them as lenses because they have a uniform shape. Yes, exactly. Intel has had problems, yes. Exactly. And the ULV machines, or rather the EULV machines that you get from ASML is right at the bleeding edge of technology. I mean, and that's kind of one of the issues that they have right now with the yields and the amount of chip availability. There's many things impacting at the same time. When COVID started, a lot of fabs pulled down on capacity because they thought that they wouldn't sell as much. Well, that was a bad idea. They actually sold more things due to the COVID thing. You have the Texas plants, of course, that broke. There was a plant that makes the chip packaging resin that had an issue and broke down. That caused a lot of backlogs. Just earlier this week, Renesas, which is a huge OEM chip manufacturer for the primarily the automotive industry, had a fire in their plant where they make the wafers, the silicon wafers. So that plant is going to be down for a month. So they're going to have very limited capacity. And I can almost guarantee you will not find a car on the market today that does not have Renesas chips in it. And just when you thought it couldn't get worse, you have that little ship getting stuck. The car industry is really hurting. Yes, it's gonna be hard for them to evolve the processes on the current silicon that we use. You're getting right at the limit, for sure. You also start getting into thermal issues, boundary breakdowns through electron migration. So over time, very slowly, the voltages involved in these, when you get down to those sizes of features, will start eating away at the metal layers. So when you change things, the electrons migrating might pull an atom along of metal. So, oh yeah, that's true. Static electricity. Actually, I might do that in another stream someday to show how, or at least explain my understanding of how a MOS transistor actually works, a MOSFET. That took me a long time because I can understand the whole NPN, PNP type thingy, but how does it actually work? What makes that doped areas into an electrically controllable gate? And I finally understood it just some time ago. Oh, fun story. I actually work for a space company. Well, not a space company, a large satellite operator. Yes, they use different processes. I don't know the exact materials they use, but they use different metals inside of them for the vapor deposition, for example. They also encapsulate them really hard, of course. So yes, they can't go down to the modern feature sizes, of course. You can still buy rad-hardened 386s, I think, still. I think that's what SpaceX is using, or used for a while at least. SpaceXs are really weird.